So please give me the survey, okay? Please give me the feedback, give me your feedback. So how can we improve from your side, from my side, and how can we make sure you guys get what you are supposed to learn, and also we have a very, very good learning experience. Okay, so this is anonymous. No worries, no punishment. I want your feedback. You are my friends. And we just want to make sure our learning experience is wonderful. Okay. So you will just come here and please get these two handouts, lecture 12 and lecture 13. The last time we talked about the small scale union, right? Small scale union, and for this is this edge crack quality, and we have some inequality, some requirements, small scale union, and what the condition small scale union. For this, what is the small scale union? And small scale union means that the IPM, so as long as these three conditions they are met, and we just think that the plastic deformation is not very big. So as a result, the linear elastic fracture mechanics is still valid. It is for small scale union. On small scale union, if there is no plastic, definitely LEFM works very well. If there is a plastic, but still this plastic is a small scale union, and which is constrained by these three conditions. And if this case, FEM is still working. However, if the small scale union is no longer valid, LEFM fails. The fails means that it will not give you the reasonable results. Then what should we do? And we have several things to do. First, we use the crack tip, the opening the displacement, and it is called CTOD, and CT crack tip opening displacement. And it is a delta. We use a delta to denote. And we use a delta to denote. I will draw something here. Wells, this is Professor Wells in 1960s, and he proposed this is crack tip opening displacement. I suppose this is a crack, okay? So this is original crack. So here, this is the original crack. This is our original crack. This is original crack. And under some condition, so this crack opens, and because some load, and some crack opens. So here is this is a final crack. This is a final crack at this point. So this is a crack tip. At this point, we want to see how big this delta is. How big the open is. Okay? How big the open is. So here you can see here is a crack tip. So this is the crack tip. So this is a new crack tip. So at this point, and we suppose these cracks, they are very, very sharp. Okay? They are very sharp. That means, so this crack face and this crack face, they are almost identical. But for this visualization purpose, I just draw a very, very big crack. But we only talk about the sharp crack. Do you understand, guys? The sharp crack. So this is my crack tip. Right? So this is my crack tip. So at this point, so suppose from here to here is Ry. Ry is yield strength. This is R equals Ry. So we know that. So this is a plastic. This is a plastic size. Ry equals this one. We talked about this one already. R1 equals Ry, their yield, 1 pi Ki divided by sigma y. Sigma y is the yield strength of your material. So, excuse me. At this point, right, so this is it opens here. At this point, this is the original one. Here is this. There's some plastic. And this is my new one. So here, from here to here is Ry. Ry, and what I want to know is what is the distance between this point, and from this Ry. So this is my new crack tape. This is my new crack tape. So here, so this is Ry, okay? This is Ry. I want to know this is distance, this is distance. So here is a total delta. Delta equals 2uy, because you have two phases. One is up, one is down. Okay, this uy. And how can I get this uy? And uy equals 1 theta equals pi. Why is theta equals pi? Because excuse me, I told you, and I will just assume this is a very, very sharp angle. This is a sharp crack. And a sharp crack means that, so these two guys, they are almost identical. You understand, Phil? Okay, so I just, how come I get uy? So this is my x, so this is my y, and from here, I just want to get theta from here. So this is the theta. This is theta equals pi. So this theta equals minus pi. Minus pi. So I know. So this is the theta. This is the point I'm interested. This point I'm interested in. So this point and this point. So from this crack tape to here, so this is Ry. Ry is how big is the plastic size, plastic zone. So this is Ry. So I can use this equation, which is in the table 2.2. I'm using this one, theta equals pi. This is R equals the Ry. I can use this R equals Ry. Theta and R, these two parameters, and can determine one single point. You guys agree? So I can use what is given in the table 2.2 to get uy. And uy turns out to be the kappa plus 1 divided by 2 mu. And this ki is the stress intensity factor. And square root of r. R is the distance, right? Distance from the point of interest and to the crack tape, and divided by pi. So for here, R equals Ry, you can just plug in. And also, Ry, we have talked about this one already. Ry is closely related to your yield strength. So you just plug in, and you will have this equation, right? You have this equation, and 2 divided by Young's E prime. E prime is the effective Young's modulus, and Ki squared sigma ys. So delta equals, as I said, okay, and delta equals the crack tape opening displacement. As I said, delta equals CTOD is defined as CTOD. That equals 2 multiplied by uy. You guys agree? We just assume, so this crack face and this crack face, they are symmetric about this x-axis, and which passes, this is the origin crack tape. So that's the reason the delta equals 2uy. And we can use this equation to analytically get this uy, and then we can get this delta. So what for the copper? This is copper here. Copper is cursive. This is a this is K. Okay. This is not K. And we call copper plus 1 equals 4 minus 1 nu. And write down on your lecture notes. The nu is the Poisson's ratio. Nu here is the Poisson's ratio. And this is for plane strain. And for plane stress, and we have couple plus 1 is a 4 divided by 1 plus mu. Also, a mu is a shear modulus. A shear modulus is determined by Young's modulus and nu. I write this as a V, okay? But what I want to tell you is that this is a V. It looks like a V, but when I hand wrote it, it's very difficult to write the nu. So this is the nu we call, and this is nu is the Poisson's ratio. Any questions regarding on how did we get this is a delta? No question, right? You guys are okay, right? You guys know where other people are? Huh? Want to say something? Okay, so this is delta. And as you can see, we just delta equals 2uy, and we just have the 2 is changed to 4. And 4 divided by e prime ki squared and sigma ys. You can see, so for this delta, Young's modulus plays an important role, and also the yield strengths come into play, right? Plasticity, Young's sigma ys is the yield strength of the material. That means material property. One material parameter is one material parameter. This guy that comes into role, comes into play. So G, we know that, okay? So Ki, okay, this is Ki, and we know that and G can be written as Ki squared divided by E prime. So then this equation can be written as 4T divided by sigma ys. You can see sigma ys is a plastic parameter. So this guy is playing a very, very important role here. Questions so far? So no question, and we know, okay, this is Young's modulus. This is we have E prime is the effective Young's modulus. And based on whether this guy is a plane stress or plane strain, we have different the Young's modulus, effective Young's modulus. Now we can use this one and to describe the plasticity, fracture mechanics for this is a bigger plasticity. And in small scale yielding, for small scale yielding, and delta and Ki or G, all these three guys are okay to describe the stress field, to describe the fracture mechanics. However, for large small scale yielding, and K and Ki and G are not okay. You understand, guys? So this is the accommodation. Is this compatibility is from that means delta is okay for small scale yielding. You can see, okay, delta and Ki and G and all these three guys are okay for small scale yielding, and definitely is okay for the linear elastic. But for larger scale yielding, Ki and G are not valid. Ki and G are not valid. Only delta is okay. You understand, guys? So this compatibility is going down. This is the downwards compatibility. Delta can accommodate the small scale yielding and also the linear elasticity, but Ki and G is not compatible for upward direction. For this is the upward direction. So be very careful about this. So then we also learned these strips, this yield model, and for strips, this is the yield model assumes the plastic stress condition and the non-hardening material. Non-hardening material means that the sigma ys is horizontal. Right? This is no hardening. And the CTOD, so here is the CTOD in a through a crack in infinite plate subject to remote tensile stress is obtained. So this is the delta. Delta for this strip yield, okay? Delta equals 8 sigma ys crack length pi e log. This is SEC 2 pi sigma s. As I said, delta is used to describe the fracture mechanics for the material that has dominant the plastic zone. So as a result, sigma ys must appear in this equation. Yeah, see, this is sigma, this is delta. Right, so this is delta. So how can we simplify this? The log function, okay, we know that log function log 1 minus 1x equals minus log 1x, and which equals x, and then this equation can be obtained, and SEX equals reciprocal of 1 over cosine x, right? And 1 over cosine x, and can be written using this Taylor equation, Taylor expansion, and come here, okay? So come here. Then this equation can be used is approximate to 1 plus 1 over 2 to this explanation sign x squared. So from here, so since this secant x equals 1 over cosine x, is you are okay with this step, right? This step from here to here, you are okay, right? But for here, this cosine x, the cosine x, we can just extend this cosine x using the Taylor expansion. I go. Taylor expansion. Cosine x can be infinitely approximated using this infinite number of this is a polynomial. You can see 1 over x, log of 1 over x, right? Log, then we have log 1 over x equals this one, equals this guy. And then we can, this is log section, you can see log secant x equals log secant x equals this one, and we just plug in. So log 1 plus x, log 1 plus x equals, so this is x. So based on here. Are you guys following me? Okay. Are you following me?
Trying to.
Okay, let me repeat. So here, I did not use this one, I just give you this format where I'm going to use this equation for here, for this step. So secant x equals this one. This step is okay, right? It's just a reciprocal. And then this cosine x can be written in the Taylor expansion. Infinite terms. So this 1 over 1 minus x equals 1 plus x. And so for all other terms, I just omit. I only have this is the big term, 1 plus this bigger term. Then I log x, log this one, log say secant x, log on secant x. So this one equals log the secant x is already secant x is already given as 1 plus 2 explanation sign and x squared right? Right? And then I use this one. You can see log 1 minus x equals here. Log 1 minus x equals minus x. Equals minus x. Right? As a result, here I will have, so this is answer this. So here, this one I will have 1 x squared. You guys agree? What is a 2 exclamation sign? A 2 exclamation sign equals 2 multiplied by 1, right? You guys still remember? So what we call in English for this? Huh? Factorial? Yeah. Okay, that means say suppose I have 5 and 5 expression. This guy equals 5 multiplied 4 multiplied 3 multiplied 2 until you get 1, right? Yeah. Yes. So this is the 2 explanation set equals 2 multiplied 1, so which equals 2. That is how I get here square x squared divided by 2. So this is the log secant x. And then you can just plug in log secant x, this one, and you will have, so this is the x here, so x squared half, this is x squared, total x squared half, x squared and half. This is how I get this delta. Right? Right, okay? Is that okay? Then I just arrange this one. This is pi square 4 sigma y square sigma square, and you can just pi, this is the pi, so this is sigma y and just cancel, and finally you will get pi a sigma square sigma y Young's modulus. And also, because for the through thickness, and for the through thickness crack, ki equals sigma divide sigma square root pi a, and you can just plug in. So you can just have the ki here. And also t, and t is ki, they are related, and you can have t divided by ys. So this is how we get this delta for through thickness. And so this is the delta equals this one, right? And so this is delta, we just omit this is intermediate step, and delta equals this. And Ki E Young's yield strength equals G sigma ys. So generally, okay, generally we have this is equation, but we have this is m here. M is a factor. M is a factor. So m is around 1, and for this is a plane stress, m equals 1, and for the plane strain, the m equals 2. For different case scenarios, and we will have different factors. Questions so far? I want you guys to go through these derivations and before you go to bed today, this evening. Okay? My bottom line is that if I give you a problem, you know which equation and you should use. You have sense? I will not test your derivation, understanding of derivation, but I hope you can know that is a derivation. Also know under what condition we should use delta instead of Ki, and this is a G. As I said, for the small scale union, Ki and G are valid, but for large scale union, Ki and G fail, and then we need to use this is a delta. But delta is okay for the small scale union. Questions? No questions? The CTOD, whenever you talk about CTOD to the interviewer, for your job, when you have a job interview, okay, so the interviewer will be excited and you will get an offer very quickly. The CTOD. Michael, want to say something? Okay, so in addition to CTOD, and we have a CTOA. We have a CTOA here. So this is the alternative. This is a CTOD, displacement and original crack tip. Displacement as original crack tip. So how big it is when the crack grows. So this is delta. Okay, this is our delta. And then we have the CTOA. And CTOA, as you can see, this is the D here, this is the D here, okay? This is the displacement. So this is my new crack tip, this is my original crack tip. And then I just draw, this is two lines. So these are two lines. So this is, for this case, is a 45 and 45, but it is not the case. And CTOA is the angle. So these two lines, the form, called CTOA. And CTOA, and CTOA, and CTOA, and crack tip opening angle. Crack tip opening angle. So this is the two observations. SSY, KI, delta in predicting crack growth is okay. But for large scale union and KI fields, G fields, and only delta works up to now. And let's talk about the crack tip. This is a crack tip. So here is the edge cracked. This is a specimen. And suppose we have an edge cracked specimen. So you know 3-point bending, right? So this is a specimen, and we use the fatigue. And we use the fatigue to generate. This is a pre-existing. Is a fracture, small fracture. Then at this point, and we have a support, and at these 2 points, and we just apply the load. So this is called a 3-point bending. And for 3-point bending, and so for some instance, we call this a hinge mode. So this point is fixed. It does not move in X direction and in Y direction. But when it bends, okay, so this is also is acceleration. So this is for visualization. So this is a W. So this crack length is A. And for here, so this W minus A, we use this R. So this R is called a rotational factor, which is between 0 and 1. So this is the delta from this point and this point. So this is the delta, okay? I want you guys to follow me. So this is delta. What is the delta, guys? I just forget. Can somebody remind me? Gosh? Huh? The delta is the crack CTOD, right? Crack tip opening. This is the displacement. When the crack opens, and how big is the displacement? So this is the delta. So this delta is usually difficult to measure for us, but we can measure how big the mouse is. You guys agree? When we do this is the 3-point bending, and so this delta is very, very difficult to measure because you need to use the equipment, use some device, put the device inside this crack. But alternatively, we can measure the mouse, how big the mouse is opening. You guys agree? So that's the reason we use a V. We use a V. V is measurable by the experiments. Using experiments, V is measurable, and we can use some model to once we have the V and we know how to calculate the delta. As long as we have this A and this is R value. So how to calculate this delta? You can see, right? So this is the similar the triangle, two triangles, and delta and the V, and they are corresponding to this one and this one. and respectively. And then we also know that, let me just draw, this is a figure. And for simplicity, I only draw the half. So this is a half V. So here is the half delta. Right? You guys agree? So I know, so here, if I extend this one, and let me use the red color. If I have extended this one, it comes here. So this is a small triangle and this is a bigger triangle, and they are similar. You guys agree? Right? They are similar means that the ratio of this edge to this edge, that means half delta divided by half V equals, so this one over this to this. So this one equals, you can see R W minus A. R W minus A. So this one. This is R W minus A. However, the whole thing from here to here, so this one equals R W minus A and plus this A. Do you guys agree? Do you guys agree? So then I just write here R W minus A and plus A. So how can I write this, get this equation? Because this is a smaller red triangle is similar to this triangle. How can I know these two triangles, they are similar? Because they are sharing the same angle, right? If I know these two guys are similar to each other, means that the ratio of this bottom line, this side and this side to this side equals the ratio of this side to this guy's the whole side. So that's the reason I have this equation. So here is 1/2 and here is 1/2. I just get rid of this 1/2. That's the reason I get this equation. Understand? I just said delta is not easy to get using this in this experiment, but the V, how big the mouse is, I can easily measure, and so that's the reason this delta can be written in terms of this is R rotational factor, and W is the width of the specimen. A is the corrective. So this delta can be written in terms of these parameters. You understand, guys? The delta C, okay? So this is delta C. The C is critical. And C is a material property when the crack begins to grow. And underscore this one, delta C. Whenever you see the lower this is subscript C means the critical. That is a material parameter. Questions so far? No question? So this model is called a hinge model. We just think here is a hinge. That's the reason. So this model is called a hinge model. And then we can modify the hinge model. Why we can modify the hinge model? Because now we have plasticity. Okay. So this is plasticity. I do not know on what have you ever heard? I think you have heard this plasticity, right? In this class, except in this class, have you ever heard the plasticity in other courses? Yes. Michael, you have heard?
Yeah.
Which course?
Material science.
Oh, material science. Okay, so that's good. If you have heard this one, that's good. And so now I'm going to show you what is the plasticity. So you can see this is the curve. This is displacement and the P. So from here to here, and so ideally, as long as the P improves, the V and the displacement will improve proportionally. Okay? So you can just see this stress strain, the same thing. So this P and V, displacement versus load, is similar to the curve that is stress versus is a strain. Okay? So you can see from here to here, it is linear. We have a slope with a linear. But after this point, and so this material is not linear, but it is still the P, even though the P is moving, but the delta of the V is not changing proportionally. Okay? We call that at this point, the material starts yielding and its material is hardening. And from here to here, whenever you apply a load and you remove the load, supposedly, and you will go back along this is the curve. But, however, once your material yields, okay, without loss of generality, once the material you use, and then you want to unload this condition, remove the load, then you will go along this curve. So this curve, this straight line, and this straight line, and you will have the same, smaller, same slope. But even when the peak, when you come here to this point, when you come to P here, when P equals 0, but you still do not have the displacement is not equal to 0. And you still have some displacement. Okay? As I said, so this figure is very, very similar to the figure of stress and Iverson. Stress and Iverson, stress, strain, and stress. So it also goes this way, and yield, after you come back, it goes here. So for this diagram, so this is a plastic P. I want you guys to write down, okay? However, so this point, this is a straight line, this is a horizontal line. So this point, this one is a elastic strain. Write down for this one. So this curve and this curve are very similar. But for here, we just I like this one much better. So because this is stress, I'm talking about stress. That one is talking about force. So this is talking about strain, and that one talk about this is a displacement. Displacement is related to the strain. Do you guys agree? And the stress related to the P, to the load. Do you guys agree? And this curve and this curve, they have the same thing. So, with that being said, the delta can be decomposed into two terms. One is the contribution from elastic. EL means elastic. And second delta is from plasticity. Okay? So this is the delta can be decomposed into the elastic contribution for the delta, and also plastic contribution for this delta. Now, modify the hinge, and we only use the hinge model for the delta PL. Okay? Delta PL. This is my delta. But VL, this V is decomposed into the V here, and V equals V elastic plus V and plastic. So that's the reason why I have RPW minus A, RPW minus A plus A. Here is a VP, and this VP means the plastic deformation. The mouse is a mouse because of the plastic deformation. However, for the elastic deformation, we do not use the hinge model, and we just use delta EL. And so this one is what we just got on the previous page here. You understand that? Questions so far? I want you guys to write this down. I want you guys to write this down on your lecture notes. On the lecture notes I give you, or if there's no space on the lecture notes, you can write on your notebook. And then we look at the CTOA, okay? So CTOA, after the crack become blunt. After the crack become blunt. So from the current crack tip, the back for 2 millimeter. Okay? Back for 2 millimeter in this direction, and then you will have this is a horizontal line that intersects on this crack face on this point and intersects with this crack face at this point. Make sense? Then this is my original crack tape. This is my current crack tape, and I connect this current crack tape to this point, and then I connect this crack tape to this point. I have two lines. So this angle formed by these two straight lines is called CTOA. You understand, guys? One more time. And after you sharp crack become blunt and become bigger, okay, because of loading, and you will have a current crack tape, and then you find a point, and how to find the point, and you just draw a vertical line. And so this vertical line is 2 millimeter away from the vertical line that passes your current crack tape. So this vertical line intersects this crack face and this crack face at this point and this point respectively. All right? Then you have 3 points. These two guys and the current crack tape. Then you form this straight line and form this straight line. After you get these two lines, so this angle formed by these two lines is called CTOA. And CTOA is very similar with the CTOD. That is also a very, very good characteristic to describe the fracture mechanics. Any questions regarding this one? Now, this is because the 2 millimeter, sometimes different people is used different, when we do some experiments, right? Do you guys agree? The same thing, different people, when they measure, there is some deviation, right? So to minimize the deviation, what should we do? We should draw 3 lines, 3 vertical lines. So you can see the first vertical line is 1 millimeter away from this original, from this vertical line, which causes this is a current crack tape. So this is one line. For this one line, I have 2 points. For these 2 points, I have 2 lines. So I can get this is alpha. This is alpha for 1 millimeter. And the same thing for, I just draw another vertical line, which is 2 millimeter away from the crack tape. And same thing, I have, this is a new, this alpha angle. And thirdly, for the 3 millimeter line, I have another angle. So this is 3 angles. That's the average CTOA from 1 millimeter, 2 millimeter, and 3 millimeter. So this one, I like this one much better, much more than this one. Because for this one, we have average, and so different people's, the value is much more closer. Right? So here are some observations. For typical alloy, aluminum alloys, 700 series, the critical CTOA means 4 to 6 degrees. It means that critical CTOA means that if this CTOA reaches this value, it is going to crack. The crack will grow. Right? So CTOA appears a better parameter than the CTOD at a larger scale yielding when plastic deformation is dominant. So exactly 1250. So we have learned CTOD and CTOA, and how can we get this is a CTOA? Okay, maybe in our midterm exam, I will ask you to draw a figure to figure the diagram on how to get the CTOD and CTOA.